author of the papers are Schrader, M.E. Hickman, and Dr. Schrader will be presenting the paper.
Let's see, can I have the first slide, please? Well, as both previous speakers have pointed out, the typical industrial hydrodesulfurization catalysts that are used have been around for quite a while, and they usually consist of cobalt or nickel with molybdenum supported on gamma alumina. Sometimes, of course, tungsten is talked about also. But these catalysts have their origins, and as Russ pointed out, in pre-World War II Germany. Much progress has been made over the last 40 years in understanding these catalysts. In fact, I think in the recent years the progress is really rather remarkable, although I'm sure there's much work that remains to be done. We became interested a few years ago, however, in looking at a new class of hydrodesulfurization catalysts based on so-called reduced molybdenum sulfides. These are based on compounds that were discovered by Professor Roger Chevrel of France, who was really interested initially in their superconductivity properties. But the reason we were interested in them is that as reduced molybdenum sulfides, they emphasize the electronic properties of these catalysts. And because there was such a rich chemistry involved in them, there was the opportunity for varying some of the electronic properties of these materials and perhaps correlating this with catalytic activity. At present, we've examined over 20 Chevrel phase compounds, and the vast majority of them have been active for hydrodesulfurization. And in fact, most of this catalytic activity is greater than that of conventional MOS2 or COMOS type materials. What I'd like to do today is really summarize some of these results, emphasizing some of the structural as well as electronic relationships with catalytic activity. So first, let me introduce you a little bit to Chevrel phase compounds. There actually are several families of Chevrel phases, but the ones that we're interested in are the chalcogenides, which are based on sulfur. The basic building block here of these molybdenum Chevrel phase compounds then will be MO6S8. There are ternary metals which one can introduce into these compounds, and actually there's a very large number of ternary metals with various stoichiometries that are possible. You can classify the Chevrel phase compounds according to whether the cations are so-called large cation materials, intermediate cation materials, small cation materials, and then the binary compound MO6S8, which I guess I'll dismiss right away since we never found this material to be stable under HDS conditions. It always converted to MOS2. And in fact, you make this compound by extracting the ternary metal from some of these other ternary metal compounds. Just to look at these a little bit, the large cation materials, for example, are unique in that they exhibit no range of composition or a very limited range of composition. For example, the lead Chevrel phase compound really has only one or two stoichiometries that are really confirmed in the literature. You might make a compound with molybdenum having a 6.2 stoichiometry involved here, but really not much of a range. In contrast to that, the small cation compounds usually exhibit some type of range in composition. For example, the cobalt Chevrel phase compounds can have a variety of amounts of cobalt in them. Similarly, copper is one of these materials in which X can vary for copper between 1.6 and actually up to 4. Rare earth compounds usually fall in the range of the large cation materials. Their compositions usually are where the rare earth is in a stoichiometry of 1.2 and then MO6S8. The rare earth compounds are interesting because you can form some solid solutions with the rare earths and that you can substitute other metals to the structure of the Chevrel phase compound. And I'll come to this a little bit later in my talk. This gives you a way of systematically varying the formal molybdenum oxidation state. Just to show you the range of materials here, the lightly shaded areas here are all the ternary metals that have been confirmed as being that one can introduce into the Chevrel phase compound. And if you think of this from the standpoint of hydrodesulfurization, of course, you've got things like cobalt and nickel up here, but you've also got some other materials here that are really kind of unknown as promoters for hydrodesulfurization catalysts. And this also made these materials rather interesting for our standpoint to look at them. Well, let's look a little bit at the structure of the Chevrel phase compounds. Again, the basic building block here is the MO6S8 unit, and this is a cubic symmetry that's involved here, in which we have the molybdenum atoms here shown in green, forming a cluster of MO6, and then the sulfur atoms forming a basically cubic structure, although this cubic structure is kind of elongated along what is the ternary axis shown here. And what happens here is if you look at the molybdenum metal bond distance in these compounds, you come up with some very short distances. These range from about 2.65 to about 2.8 angstroms compared to 2.72 for metallic molybdenum. And in fact, you can actually decrease these molybdenum bond distances by feeding in the ternary metals into the system. In fact, really what you're doing here is adding electrons to the molybdenum structure here, and this decreases the bond distance. This, again, then emphasizes the fact that these are really reduced molybdenum sulfides, and you can see this in the XPS data. You can confirm this, that all of these molybdenum oxidation states here are considerably lower than what you have for MOS2. Now, when you start to build up a small cation or intermediate cation or large cation materials, you can arrange these MO6-8 clusters in various degrees, various ways. For the small cation structures, you actually form channels in which you can put the small cations, and these are somewhat delocalized. Thermal motion here that's involved indicates that these are, you can consider these really channels in the structure. And this probably is the reason why you can introduce various stoichiometries into the Chevrel phase compounds. However, when you get up to the large cation materials, you don't have that opportunity anymore. These large cation structures here, now these are in blue here, the large cations or the ternary metals here, are pretty much localized. And this gives great stability to the structure. In fact, all the Chevrel phase compounds really are very stable because of this, the bond distance here, the metal molybdenum sulfur bond distance here are relatively short, and the structure therefore are really rather stable materials. Well, it turns out, as I pointed out before, that these are these Chevrel phase compounds. Actually, there are large families of these. And Chevrel himself has postulated that you could build up a very rich solid-state chemistry using these compounds and using these MO6 clusters. Here are chalcogenides here that we're looking at, but if you get into oxides and other materials, you can actually build up a lot of edge-sharing materials that exist throughout the whole solid state. Bob McCarley at Iowa State has built some metal oxides that have some very interesting structures here. This has given rise to the description of these Chevrel phase compounds as involving little bits of metal, and I think that's kind of a nice way to look at the structures of these materials. And it also emphasizes the fact that these are reduced molybdenum compounds, and one can really increase the metallic nature of these compounds by adding ternary metals to the materials. If you want to do a simple calculation for the oxidation state of the Chevrel phase compounds, if you did just do this in formal oxidation states, assuming accepted values for the ternary metals and -2 for the sulfur, you'd come out with molybdenum oxidation states varying between 2 and perhaps 2 2/3 here. If you do the XPS data, which I'll show you a little bit later on, also you can clearly see that these oxidation states are lower than what you would have for conventional hydrodesulfurization catalysts. And as Russ has pointed out, this gives us a way of really getting into this, these reduced molybdenum oxidation states that many people have correlated with catalytic activity for hydrodesulfurization. Well, let me tell you a little bit how you prepare Chevrel phase compounds. They're somewhat difficult preparations. They're all high temperature solid state syntheses. Do these in sealed quartz tubes, sometimes backfilled with argon gas. There are really two ways for doing this. You can start out, you can do what I'll call preparation 1 or preparation 2. Basically, you choose the preparation method in order to get the most pure material. Preparation method 2 here does give you usually higher surface area materials, okay, than preparation 1. But these are all highly crystalline materials. As I'll show you, they're low surface area materials. In our work, we were very interested in having highly pure materials because one of the things you always want to avoid here, of course, obviously, is making MOS2. And we've succeeded in doing that for the studies that I'd like to report to you today. Just for sake of comparison, we've also made MOS2 compounds and the topso type phases here for models for promoted catalysts for comparing the activity with our Chevrel phase compounds. Well, let me tell you a little bit about the characterization of the Chevrel phase materials. As I mentioned, they're low surface area materials. Okay. Here again, using this classification of large, intermediate, and small cation compounds, the fresh materials usually have surface areas less than about 1 square meters per gram. This may change a little bit after they're used in thiazine hydrodesulfurization here for 10 hours. Some of them show increases, some there is not really much change that's involved. Again, the compounds that we're comparing here are of higher surface area. Now this presents us with a dilemma now when we want to report catalytic activity. So what we have decided to do is report our catalytic activities on the basis of surface area, normalizing these to surface area. But of course we realize that catalytic activity doesn't always correlate with surface area. So what I'd like to suggest today is not a precise ordering of the activity of Chevrel phase compounds, even with respect to the model MOS2 compounds, because again there's this uncertainty between surface area and the number of active sites. But what I'd like to indicate is that the activities appear to be comparable between these model MOS2 compounds and the Chevrel phase compounds. Well, again, if we're going to try to use the Chevrel phase compounds to look at the relationships between solid-state chemistry and catalytic activity, it's very important that we have pure phases. I'll go through these slides rather quickly. All I'd like to point out is that using X-ray diffraction, we really never could see any other phases being present. Some of the stoichiometries that you prepare these materials at make you start to worry about whether there might be some metal present in the system. We were never able to see that. With X-ray diffraction, we were never able to see any crystalline MOS2 in any of the compounds. Using laser Raman spectroscopy, we searched for any type of amorphous or non-crystalline MOS2, and of course using the Raman technique, you can find poorly crystalline MOS2 very well. And in fact, we never saw any poorly crystalline MOS2 except for 2 compounds in the fresh tin Chevrel phase compounds and the used tin Chevrel phase compounds. You can see some MOS2. And the cobalt Chevrel phase compounds also produced some MOS2 in the used catalyst, although the initial catalyst did not have any MOS2 present in there. Here's typical XPS data. And actually, it's not very typical in that the vast majority of the Chevrel phase compounds did not demonstrate any change in the molybdenum oxidation state as a result of use in hydrodesulfurization. Most of the molybdenum 3D 5 halves peaks are around 227 EV, 227.7 I think EV, compared to 228.9 I guess for MOS2. There were a few compounds such as the cobalt Chevrel phase compound that did show some change in the molybdenum oxidation state after use, and this is again reflecting probably oxidation at the surface to form some MOS2. But what I want to leave you with is the idea that these Chevrel phase compounds are very stable. You would think that structurally, you would think that from the way they were made, and our results with a lot of characterization really shows that very few of them undergo bulk transformation to any other phases. And what you put into the reactor is pretty much what you get out of the reactor under our studies for thiazine hydrodesulfurization. and benzothiophene. This is a small illustration of our microreactor type system. Thiophene studies were done at about 400 degrees C. Benzothiophene, which I won't tell you very much about today, studies were done between 250 degrees C and about 500 degrees C. Studies done for as long as 40 hours in some cases. Well, let me just show you some of the general relationships for the Chevrel phase compounds. Again, on most of these slides, I'll have the model compounds MOS2 and the cobalt topso type phase shown here. I know the topso phase is the top one shown here. For the small cation materials, most of them are more active in the MOS2 phase. However, they were not quite as active as the cobalt promoted phase. What we're kind of surprised about is that when you looked at enough of these here, you'll find out that the cobalt phase is not the Chevrel phase is not particularly highly active compared to other ternary metals. And when one gets into some materials like iron and copper, these are really rather strange materials to think as promoters, if you want to call them that, for hydrodesulfurization catalysts. But the small cation materials were basically probably the least active Chevrel phase compounds, even though we might have thought them to be the most active Chevrel phase. When one goes up to the intermediate cation materials, we were really rather surprised, because when one starts to look at things like silver and indium, there's really not much basis here for thinking of these as being promoters. But again, if you think of the crucial idea here as being the oxidation state on molybdenum, I guess, which several of the people today even have talked about, what we're really doing here is just feeding electrons into the molybdenum. And what we're doing here is increasing the number of d electrons and looking at more reduced phases. So in essence here, maybe it isn't so surprising that some of these promoters are successful. One of our most successful Chevrel phases still remains this Holmium phase, which has catalytic activity 2 or 3 or maybe even 4 times greater than the cobalt topso type compound. Tin, lanthanum, a lot of the rare earths are very active Chevrel phase compounds. If you try to just get a rough look at these rare earth compounds here, lanthanum, lutetium, dysprosium, all of these again are rather active compared to the Chevrel phase, compared to the conventional catalyst. Lutetium was a little bit disappointing here. We don't really understand why some of these are not as active as others. But again, most of them are of comparable activity on a per unit surface area basis. There are some averages you can calculate here, and again, just to emphasize these, that the large cations compounds are the most active, and the intermediate cations, and then the small cations. This is an average of some of the compounds that we've looked at for thiophene hydrodesulfurization. The general trends that are shown there. Well, we've been quite interested over the years to try to compare, or try to sort out what the reasons for this activity is, and to try to examine the stability of the catalyst. And without going into this great detail here, there are some compounds for which there does seem to be kind of a promotional effect. Here, where we've looked at consecutive pulses of thiophene going over the catalyst here, some of the catalysts do show some gradual deactivation here, but there are some phases, for example, the cobalt Chevrel phase compound, that does undergo some type of activation. What we think this is really, again, a surface oxidation of this cobalt Chevrel phase, in which we are forming MOS2 on the surface of this catalyst, okay? And this is one of the few catalysts that appears to do this. But the small cation Chevrel phase materials are these materials in which there's a good deal of delocalization of the cation. There's mobility of the cation. And what we think is happening here, and XPS confirms this, and Auger confirms it, that there's a retreat of the cobalt away from the surface in some of these compounds, and you tend to form MOS2 on the surface. And that may be as a result, the reason why this catalyst is looking like it activates. Some other compounds, we really don't understand what happens with some of these. For example, the tin Chevrel phase compound also undergoes kind of an activation here. Even the lead Chevrel phase does too. There doesn't seem to be much motion of the ternary metals for these type of compounds. What I should point out is a little bit of studies with benzothiazine, and again, I regret that I don't really have too much to say here during this talk about this, but again, the activities here for this lead Chevrel phase compound isn't too far off from what the conventional cobalt-promoted Chevrel phase compound looks like. We've also done a series of studies where we've tried to look at various ways of preparing the Chevrel phase compounds and looking at these stoichiometric differences that are apparent in the literature when you start worrying about preparing pure compounds. And I guess with the limited time I won't talk very much about this, but some compounds like the rather active lead Chevrel phase materials, there doesn't seem to be much difference in terms of the amount of molybdenum metal you have in this catalyst. Both of these phases here give very similar X-ray diffraction patterns, very similar Raman vector in terms of looking for MOS2. So preparation doesn't seem to have much effect on those compounds. Other materials like tin, you can quite strongly influence the hydrodesulfurization activity by changing the amount of molybdenum metal you have present in the system here. And for some other, although here these compounds appear to be rather stable, other compounds like cobalt, again there's some influence here on the composition of the amount of the composition here, the amount of cobalt you have in the system. And this is also dependent a little bit on how long you have the material in the reactor. But again, this is a phase that was not particularly stable. Well, we've started to be able to relate some of the catalytic activity to the solid-state chemistry of these materials. And one of the things that I'd like to again point out, which I've alluded to, is the ability of some of the ternary metals to delocalize in some of the Chevrel phase compounds. The large cation materials, there is not much delocalization. These structures are very stable. The small cation materials are materials in which there's some mobility of these small cations, such as cobalt or copper. And we think this is very strongly related to the stability of the materials during catalytic reactivity. You can see this structurally, or you can see this very clearly when you start to make a plot of, for example, the rate of thiopene hydrodesulfurization versus this delocalization. Here are all these small cations that can move through the structure, and at least in one case here with the cobalt compound, we've been able to see this cobalt material retreating down into the bulk of the catalyst and some formation of MOS2. But the most active materials are also the most stable materials. For example, holmium, in which there's very little delocalization of the ternary component, is a material which has probably the highest hydrodesulfurization activity of those that we've looked at so far. So this is a material in which these reduced molybdenum oxidation states are likely to stay around during hydrodesulfurization. And clearly, these seem to correlate with catalytic activity. In fact, we embarked on studying a series of Chevrel phase compounds in which you can form solid solutions of Chevrel phases involving the lead and lutetium Chevrel phase compound. And really what's happening here is that you are able to displace some of the lead large cation ternary metals with the lutetium. But there's a difference in the oxidation state on the lead and the lutetium. And what one can do here then is systematically vary the molybdenum oxidation state for the Chevrel phase compounds. These catalysts are rather stable over rather long time periods of reaction. And what one finds here is that the most reduced Chevrel phase compound is the one that is the one up, no, that's not the most reduced one. I guess I better go to my next slide here to show you what this really is. Here is using these lead lutetium Chevrel phase compounds, and you can calculate the molybdenum formal oxidation state. And here what we've plotted is the rate of thiopene hydrodesulfurization. If you were to put MOS2 on this graph, it would be out here someplace, and its activity would be lower, okay, than what's here. So we avoided the temptation here of trying to draw a volcano plot here, but it does look like that there is some maximum in the catalytic activity. So if one starts out with a molybdenum 4 plus oxidation state someplace, again, like I say out here, and as you reduce these compounds, you would go through some type of maximum. We don't know where that maximum is. Again, some people in the literature have pointed out that the idea that molybdenum 3 plus is what one wants to have for high catalytic activity for hydrodesulfurization. But it does appear that if you can relate this molybdenum formal oxidation state for these Chevrel phase compounds to the rate of thiopene hydrodesulfurization. So that we think is kind of an interesting relationship. There's only one slide I think that I will talk about furthermore just before going to the conclusion here, skip a little bit here. The other thing that I'd like to point out for the Chevrel phase compounds is that they're rather selective catalysts, and that if you look at the ratio of HDS to hydrogenation, just using 1-butene is a very simple molecule to look at hydrogenation. These catalysts are rather selective, and that they preferentially do a lot of hydrodesulfurization compared to hydrogenation. So here's the comparison with the model compounds. As you can see, some of these very active Chevrel phase compounds don't do very much hydrodesulfurization, or do very much hydrogenation. I think I'll just skip these ones and talk a little bit about the mechanism and go to the conclusions here. Just to summarize, Chevrel phase compounds are active hydrodesulfurization catalysts. They're at least comparable to the MOS2 based catalysts. As I just mentioned, they don't do very much hydrogenation. The most active Chevrel phase compounds are the large cation materials, followed by the intermediate and the small cation material. A large number of these ternary metals are kind of unconventional promoters. So this emphasizes, again, the importance of the molybdenum oxidation structure state. The bulk structure of the Chevrel phase compounds is stable for the vast majority of the compounds. Chevrel phase catalysts exhibit reduced surface molybdenum oxidation states, which have various degrees of stability with respect to oxidation under hydrodesulfurization conditions. Again, the large cation compounds are stable, while some surface oxidation occurs, particularly for the small cation materials. For example, as I mentioned before, for cobalt and perhaps even copper is one of these in which a little bit of surface oxidation occurs. Well, we're continuing our studies of Chevrel phase compounds, and again, as I pointed out, that they're interesting materials in that you can systematically vary the solid state chemistry of these compounds and look at the effect on the catalytic activity. What we wish they would do is have a little bit higher surface areas, and we are working on some techniques for increasing these surface areas, although we haven't been able to do this much more successfully than increase the surface areas by a factor of 10 or so, which obviously would make them interesting, I guess, from an industrial standpoint, or even maybe one would even have to have higher surface areas than that. But again, I think they're interesting compounds because they do show the importance of having reduced molybdenum oxidation states for hydrodesulfurization. Thank you.
Dr. Richard Adams from the chemistry department was instrumental in developing some new mixed metal sulfide clusters. The catalytic and characterization work that I'll be talking about was done at the Department of Chemical Engineering.